So for this video, we're going to look at a different type of covalent structure. We've previously gone into detail about simple molecules. We've spoken about how they have strong covalent bonds between the atoms, but weak intermolecular forces of attraction between the individual molecules. Giant covalent structures, on the other hand, are made up of many atoms with strong covalent bonds between them. They tend to have very high melting and boiling points because of the energy that's required to break these bonds. And we have two specific examples of these giant covalent structures that we will go through, where we will talk a bit more about things like electrical conductivity. And the two examples we will look at are structures made up entirely of carbon. One of them we know as diamond and the other as graphite. We're going to have a look at diamond first. Diamond has a structure where each carbon atom is covalently bonded to 4 other carbons. And if you think about an actual atom of carbon, it has 4 electrons on its outer shell, and so it can form up to 4 covalent bonds. So this is a bit like what we saw with methane, where we had a carbon atom which was bonded to 4 hydrogens. This time we have a carbon atom forming bonds with other carbons. And if we look at a kind of simplified 2D arrangement like this, we have an arrangement where each carbon atom is bonded to 4 others, and this is continuous. So all of these ones will be bonded to 3 others, and this will continue to a point where we have billions of these atoms. So it is quite similar to, I guess, an ionic structure in that respect, to an ionic lattice. Now, because of this very rigid structure, diamond is very hard, and so is good for strengthening cutting tools like drill bits. The melting point, as you can imagine, is very high because of many strong covalent bonds which take a lot of energy to overcome. Diamond also doesn't conduct electricity, and this is because there are no ions or electrons which are free to move around. The atoms in diamond, the carbon atoms, aren't charged, nor are they free to move around, and the electrons are involved in bonding and so aren't free, and so can't carry electrical charge. Diamond is therefore non-conductive. The next giant covalent structure we're going to look at is something called graphite. Graphite is similar to diamond in some ways and is different in others. The first thing to say about graphite is that each carbon atom is bonded covalently to only 3 other carbon atoms. We have this arrangement where there are sheets of carbon atoms. This is one sheet, this is another, and the atoms within the sheets, or within the layers even, are covalently bonded to each other. But there are multiple sheets, and although the bonds between carbon atoms in the same sheet are very strong, there are no covalent bonds between the layers. The only thing holding these separate layers together are weak intermolecular forces, and because of this, the separate layers are not held in position and are more or less free to move over each other. And so because these layers can move over each other, this gives graphite its property of being soft and slippery, and so it can be used as a lubricating material. A lubricant is basically something which reduces friction. Now, despite each carbon atom having one less covalent bond than diamond, these bonds within each layer are still overall very strong, and so a lot of energy is needed to overcome them and to break the bonds. For that reason, graphite has a very high melting point. Now, looking at electrical conductivity, carbon has 4 electrons, which can be shared, 4 electrons on its outer shell, that is, which can be shared with up to 4 other atoms to form up to 4 covalent bonds. But the carbon in graphite only form 3, so these 3 are involved in bonding. But what that means is, for each carbon, there is 1 electron which isn't used to form a covalent bond. And this electron is essentially free to move. And we say that these electrons are delocalized. They're delocalized electrons, and they are free to move. And because they're free to move, they can carry electrical charge. Because graphite has the property of being electrically conductive, this means it can be used for things like electrodes, and I guess for other materials which are required to conduct electricity. I'm going to finish off this video by looking at a final structure called graphene. And graphene is quite similar to graphite. As we've said, graphite is made up of these sheets of carbon atoms, and graphene is essentially a single sheet of carbon atoms arranged as hexagons. So it's only 1 atom thick, actually, from top to bottom, and it has exactly the same bonding arrangement as the carbons in graphite. Because of these covalent bonds, graphene is very strong, but because it's a single layer, it's also very light, so it has an ability to strengthen materials without actually adding too much weight. Also, in a similar way to graphite, graphene can also conduct electricity because of the delocalized electrons being able to carry electrical charge. Therefore, graphene has its uses in electronics, and I guess any other use which requires a conductive material which isn't too heavy.